So I know what you are all are thinking. It's like, well, all this calculus stuff is well and good, but I really want to work with calculus and logarithms, right? So you're in luck. Today we learn how to do calculus with logarithms. But before we get into the calculus side of things, we're going to do a quick review of some basic things that you should already know about logs. The one thing you really need to know about logs, if there's only one thing, is that it's the inverse of exponents, right? Y equals log base b of x is the same thing as b raised to the y equals x. Logarithms are a function that are designed to solve for the exponent in an exponential equation. So if you're trying to graph something like y equals log base 2 of x, and you're at a loss for how that graph looks like, then the best thing to do is to apply that definition and say, well, I know that 2 raised to the y is the same thing as x. So I'm going to let y be my independent variable, and I'm going to pick values of y, and I'll figure out what x is. For example, if y equals 1, then 2 to the 1 equals 2. If y equals 2, well, 2 to the 2 equals 4. If y equals 3, well, 2 to the 3 equals 8. And of course, y equals 4 means that 2 to the 4 equals 16. That's going to be way over here. What happens to the left? Well, we've got when y equals 1, we get an x value of, I'm sorry, we already did y equals 1. When y equals 0, 2 to the 0 equals 1. When y equals negative 1, 2 to the negative 1 equals 1/2. 2 to the negative 2 equals 1/4, 1/8, 1/16. The smaller y gets, the closer x gets to 0, but it never quite gets there. So logarithms have these, what are they called? Vertical asymptotes, always, right? And by default, the vertical asymptote is at x equals 0. And your basic transformations of graphs can shift that left and right. Like if we had, instead of x, we had x minus 2, for example, that would shift everything to the right too, including our vertical asymptote. So that's something that may or may not happen to you in the future. By far, the most important base is not 2, like we just saw, but e. Remember that this is the same thing as the natural log of x is the same thing as log base e of x, where e is some constant. It's approximately 2.71828. But it's irrational, just like pi. It's something a little less than 3 instead of something a little bit more than 3. So we know that if y equals the natural log of x, that means that e raised to the y equals x. And we can do the same sort of thing. We're going to find that it's going to have the same basic shape. Instead of the x-intercept is still going to be at 1. When y equals 1, we're going to get 2.8 or 2.7 instead of 2 as we did before. So basically it's going to have that same basic shape, but it's going to maybe shoot off to the right a little bit faster. Something along those lines. Not a huge difference between these two graphs. So if we're going to try to evaluate some expressions, these logarithmic expressions are all base e. So what can I raise e to get 1? That answer is, of course, 0. What can I raise e to get an answer of 0? Well, we just talked about that vertical asymptote, so this is undefined. Log base anything of 0 is always undefined. What can I raise e to get e? That's simply 1. What can I raise e to get e squared? Of course, that's 2. What can I raise e to get the fraction 1 over e? That's the same thing as e to the negative 1, right? And then what can I raise e to get the square root of e? Well, that's, of course, the same thing as e raised to the 1/2. All right, so again, when we find the log of a number, we're asking for that mystery exponent that we can raise the base to get that number, that given argument. And then you should probably, you should definitely know these. You probably remember them. And they're related to the properties of exponents. If you're taking the log of a product, you can take the sum of the two different logs. If we're taking the log of a quotient, we can take the difference of the two logs. And then if you're taking the log of an exponential expression, we can bring that exponent out front. It's almost like the power rule, but it's not. This is not a calculus rule. None of these are related to calculus. These are all just related to properties of exponents, and consequently, they are properties of logs. All right, so a pretty standard sort of log question. Again, we haven't gotten to the calculus side of things yet, is can we use these properties of logs to evaluate expressions? So if I happen to know that the natural log of 2 is approximately 0.693, then maybe without a calculator, I can approximate the natural log of 8. Well, I know that 8 is the same thing as 2 cubed. So I can actually use this property of logs to say, well, I'll pull that 3 out front, and I'll take 3 times the natural log of 2. And I happen to know that the natural log of 2 is approximately equal to 0.693, so then I can just multiply that out. I'm not going to do that part because of time, but you guys know how to multiply, I assume. Again, using this given information, how can I get a 5? Well, 25 is 5 squared, right? So that must mean that I can rewrite this 5 as the square root of 25, which is handy because that means I can bring that 1/2 out front. And we'll just take 1/2 of the natural log of 25. And again, I happen to know that the natural log of 25 is approximately 3.219. So you just divide that by 2 and you get your answer. Sometimes we have to use both of these values. You might notice that 100 is the same thing as 25 times 4, but 4 is the same thing as 2 times 2. So we can rewrite this as the natural log of 25 plus 2 times the natural log of 2. And since I know that the natural log of 25 is approximately 3.219, and I know that the natural log of 2 is approximately 0.693, we've turned our logarithmic expression into something that we can evaluate using arithmetic. All right, so that's just using some properties of natural logs. We're going to do that more generically here with some variables. Same idea though. We can turn a product into a sum. So natural log of x times y times z is the natural log of x plus the natural log of y plus the natural log of z. If we have multiple things going on, just work your way from the outside in. This is the same thing as, well, maybe the easiest way to do this problem actually is to say, well, we've got x plus 1 squared that we're taking the cube root of, so that's going to actually be the same thing as raising it to the 1/3 power. So maybe I'll just start by saying, well, 2 times 1/3 is 2/3, and then we'll just have a one-step problem. Bring that 2/3 out front, the natural log of x plus 1. We don't do anything like distributing the natural log. That doesn't make any sense. We're not multiplying natural log times anything because natural log isn't a number that we can multiply. Natural log is a function. We are taking the natural log of x plus 1. And since this is not a product or a quotient, x plus 1 is 2 separate terms, there's nothing else we can do there. Here we've got a product, natural log of 4 times b cubed. So we can change that product to a sum, natural log of 4 times natural log of b cubed. You can leave this as natural log of 4, but we know that 4 is 2 squared, so maybe I'll write this as 2 times the natural log of 2 in the spirit of expanding as much as possible. And this 3 can be pulled out front as well, and that might be the most expanded version of this answer. When we have fractions, remember there's subtraction, a little rhyme for you there. So anything that's on the top is positive. So natural log of z is positive, natural log of y plus 3 is also positive. But the natural log of wx to the 4th is negative because it's in the denominator. So now we can expand out this denominator a little bit more. Bring that 4 out. And we've got natural log of x, wx, but of course we can expand that a bit more. Again, don't try to expand this y plus 3. That's not going to help. But negative 4 natural log of w. And this is plus here, but we're also multiplying it by a negative 4, so I'm going to go ahead and say minus natural log of x. Minus 4 natural log of x. So notice anything that shows up in the denominator is going to have a negative in front of it. Anything that shows up into the numerator is going to be positive out front. So that's a nice little thing to double check. So moving right along with our blast from the past here, we're going to go ahead and condense. That's the opposite of expand, right? We're going to rewrite using a single logarithmic term. Okay, so this first step would be, we would say, well, the 3 can be turned into an exponent. And this 2 can be turned into an exponent, and this 4 can be turned into an exponent. And then, just like before, anything that's positive should be in the numerator, anything that's negative should be in the denominator. So we've got a single logarithmic expression of the fraction x cubed z to the fourth over y squared. I can't tell you how many times I've seen people put natural log of the numerator divided by natural log of the denominator. That's not okay. That's not the same thing. We're taking the natural log of a single fraction. All right, here we've got parentheses. Maybe I'll hold off on that 2 for now, and I'll just condense what's inside. Anything that's in the numerator should be positive, right? So the x is a positive natural log, so that should show up on the top. And then we've got negative natural log and negative natural log, so these two guys are going to show up in the bottom. Again, notice that I'm only writing one natural log. Do not put the natural log on the top and the bottom. And then we have the 2 is going to square everything. So we've got the natural log of, in the numerator, x squared. In the denominator, you can distribute these together and get x squared minus 1 and square x squared minus 1. So maybe I'll do that. I'll multiply x plus 1 times x minus 1 to get x squared minus 1, and then I'll square that. Again, that's the squaring coming from here. We could have also, if we preferred, we could write it like this. It's really up to you. It's the same thing. All right, numerical problem here, so nothing really different. We're just going to bring that 1/2 as the exponent. Well, raising to the 1/2 is taking the square root. And 1/3 is going to become the exponent. Well, raising to the 1/3 is taking the cube root. And I know what the square root of 25 is. I know what the cube root of 27 is. And I know that I can condense this a little bit more. 5 times 3 is actually just 15. So this is a much simpler way of writing the same more complicated expression. And then lastly, we've got a subtraction, so it's going to turn into a fraction. But before we do that, let's deal with that exponent, right? It's a coefficient now, but we can turn it into an exponent. So let's hold off on that subtraction turns into a fraction. And, well, maybe I'll hold off on the exponent as well and say, well, actually, we can condense what's inside the parentheses. So that plus means the natural log of b plus the natural log of c can turn into the natural log of the product, natural log of bc. And then we can apply that 1/2. So that's going to be the natural log of the square root of bc, right? Raising something to the 1/2 power is the same thing as taking the square root. And then the subtraction becomes a fraction. A single logarithmic expression, please. Don't put natural log on the top and the natural log on the bottom. That's going to be wrong every single time. But the numerator is a plus 1. The denominator is root bc. And that should be your fully condensed expression.